So in this example, we're going to look at a derivative involving trigonometric functions and the repeated use of the product rule. So it says f of x equals negative secant x tangent x plus e, Euler's number, times sine x cosine x. It says find the derivative. So we're looking for f prime of x, which means we need to take d dx of this whole piece here, which is the opposite of the secant of x times the tangent of x plus e, Euler's number, times the sine of x times the cosine of x. And we're going to start to show less detail than we have in previous videos. So I know that I'm going to take the derivative of the individual pieces inside the parentheses. They're separated by a plus, and I know that I can take, if I have the derivative of a sum, I know I can take the sum of the derivatives. So I'm going to look at the first term, the first expression first. I have negative secant x times tangent of x. And when I look at this, what I want to recognize is I have a product, and I have the constant multiple of a product. So this is the same as negative 1 times secant tangent. And we know that the derivative of a constant multiple of a function is the constant multiple of the derivative. So I'm going to take that negative, or that negative 1, and hold it out in front, and take the derivative of the functions that that constant multiple is attached to. So now I look at the secant times the tangent, and I recognize I have the product of two functions. So I'm going to use the product rule, and the product rule says take the derivative of the first function. And the derivative of secant, we discovered, is the secant times the tangent. Derivative of secant is secant tangent. There should be thetas in there instead of x's. I just noticed that. So derivative of secant is secant of x times tangent of x, and the product rule says take the derivative of the first function times the second function, so it'll be times the tangent function. And then the product rule says plus, add to that, now take the first function, take the secant function, secant of x, and multiply it by the derivative of the second function. And the derivative of tangent is secant squared. So secant times secant squared of x. So that takes care of the first one. And now I need to close off a parentheses so that this minus sign is distributed into the product rule that happened right here. And then I go plus, and hey, I have a constant multiple of a function. So it's going to be the constant multiple times the derivative of the function. But I have a product of two functions, so I'm going to take the derivative of the first function using the product rule, and the derivative of the sine is cosine. And the product rule says multiply that by the second function, so multiply it by the sine, and then go plus. Now take, I accidentally erased that. So plus, now take the first function, which is just the sine of x, and multiply it by the derivative of the second function. And the second function is the cosine function, and the derivative of cosine is minus sine. So it's going to be times negative sine of x. Close parentheses so that the e is distributing into the product rule that I use to differentiate the sine times the cosine. Equals. Now we want to see if we can clean things up a little bit. I have secant times tangent is secant of x times the tangent squared of x plus secant times secant squared is the secant cubed of x, close parentheses, plus Euler's number times cosine is cosine squared of x, plus minus is going to be minus sine times sine is the sine squared of x, close parentheses so that e distributes into both terms. And now we want to look at what we have going on here. So right here and right here I can do some cleanup. And the tool I can use is the Pythagorean identity. So we learned in trigonometry that the sine squared of x plus the cosine squared of x is equal to 1. So if we subtract the cosine squared from both sides, we wind up getting that the sine squared of x is equal to 1 minus the cosine squared of x. And that means I can replace the sine squared here with 1 minus the cosine squared and get everything here in terms of cosine. And if I take the Pythagorean identity and divide both sides by the cosine squared of x, cosine squared of x, cosine squared of x, pull my fraction bar out, I get sine squared over cosine squared is tangent squared of x, plus cosine squared over cosine squared is 1. That should be an x, poorly written x, equals 1 over the cosine squared is the secant squared from trigonometry. So the tangent squared is equal to, subtract 1 from both sides, we see that the tangent squared of x is equal to the secant squared of x minus 1. So I can come up and make some substitutions. So negative, parentheses, secant of x times parentheses, the tangent squared can be replaced with the secant squared minus 1. So I get the secant squared of x minus 1, close parentheses, plus the secant cubed of x, close parentheses, plus Euler's number E, times the cosine squared of x minus parentheses, the sine squared can be replaced with 1 minus the cosine squared, using the Pythagorean identity from trigonometry. And then close the parentheses because we're distributing E into every term. And then simplify a little bit. So we get the opposite of parentheses. The secant times the secant squared is the secant cubed of x, minus the secant times 1 is the secant of x, plus secant cubed of x, close parentheses, plus Euler's number times, here you get the cosine squared of x, distribute the minus sign in, we get minus 1 plus the cosine squared of x, close parentheses, and we can clean things up just a little bit more. The opposite of secant cubed plus secant cubed is 2 secant cubes of x minus a secant of x, close parentheses so that the minus distributes in, plus Euler's number times cosine squared of x plus cosine squared of x is 2 cosine squareds of x minus the 1, close the parentheses. And if I look at this, it looks like I've cleaned things up about as much as I can. I've rewritten everything in the first parentheses in terms of the secant function. Everything in the second parentheses is written in terms of the cosine function. That's pretty clean. We could look and see about using additional trig identities, but I don't think that's going to be necessary. We could, if we wanted to, factor a secant of x term out of this one, but this is probably good enough for government work. Good enough.